Part 8.3 Growth Functions. So now we want to do the real analysis, theoretical type analysis work. First, let's look at the formula between running time and the number of basic operations, the relationship. Why we can use the number of basic operations to measure the running time. How good is that method? We want to look at that question first. All right. Notations. We want to use T function, capital T function, T of n for the running time, the real execution time, so the direct measure running time. Then we try to do the indirect measure. That is counting number, C of n, number of basic operations. We want to see what is the relationship between these two numbers. Another notation we want to use, execution time of one basic operation. What's that? There should be some number, right? Here we use C up, sub up, subscript up. Now let's look at the formula. When we write the formula, we take an approximation approach, because it is very hard to represent the execution time precisely. So we will use approximation way to measure. That approximation formula is this. T of n, the real execution time, approximately equal to the real execution time for one basic operation. Then we multiply the number of basic operations. It's straightforward. Thus, approximate. Why? Because here, think about why this is not exact equal. It's approximate. Because here we only consider basic operation. Do we need to consider non-basic operation? Right? Here, there is certain amount of time used for non-basic operations. So we didn't count, so that's why it is an approximation. All right. Then from this formula, you can see the relationship between these two numbers, proportional. That relationship, proportional by a constant number. Then, because after we see this relationship, then we can measure running time indirectly using this C function. So then, that's the counting number we can use for basic operations. All right. Next, so let's closely look at this approximation approach. We need to do approximation in many steps. So in computer science, we have to do a lot of approximations. Most of the time, we cannot do things precisely. All right. But when we use the approximation approach, we should use it correctly. So in this part, I want to describe what is the correct way. First, our observation. So let's make our observation on the whole procedure of your algorithm. First, our observation, efficiency of algorithm is reflected when the input size is large. That's an important observation. how efficient is your algorithm? You can see that better and better when the input size is larger and larger. In other words, when the input size is relatively small, you cannot directly see how efficient it is from your theoretical analysis. Why is that? Yeah, so let me describe it. Because there is something called overhead. Overhead, okay? When the input size is small, you need to do some work. Overhead means the preparation work. You need to do some preparation work to, arrange a lot of resources, put things here and there, get things ready. So it takes a lot of time. Yeah. But when input size is small, the overhead part will take out a large portion of your total running time. So then your theoretical analysis will not give you a good estimate. But when the input size becomes larger and larger, the overhead part, we will spend the same overhead part, but that percentage will be smaller and smaller. Finally, very small, we just ignore it. Yeah. When the input size is larger and larger, we will ignore the overhead part. Okay? Yeah. Because the percentage is so small, so we don't need to look at it. So that's why we should mainly look at the large input case, not small input case. Yeah. That's the first observation. Yeah. Another observation for small input sizes. Yeah. So when you compare two algorithms, which one better, which one worse, if you just consider the small input sizes, you may not get the correct result. The reason is the overhead could be different. The faster algorithm may need a larger overhead. The slower algorithm may just need smaller overhead. So when you compare two algorithms for relatively small input sizes, the less efficient one probably performs better than the better algorithm. That could happen. Yeah. So that's another good comparison. So do not do it for the small input sizes. Yeah. All right, conclusion. Yeah. When we do analysis on algorithms, we should focus on large inputs. Okay? Yeah. And we can ignore the performance or efficiency of the algorithm for small inputs. Yeah, we can ignore that part. Less important. Yeah. All right. So this conclusion will be very useful in our later discussion. Yeah. All right. To do that, in the formal way, yeah, because we need to do the formal mathematical work. To do that in a formal way, we need to introduce special notations. Special notations. Yeah. So in our part B, we will focus on these special notations. Yeah. Yeah. All right. Then we can get a very good description, scientific analysis. Yeah. All right. Next. Ignore unnecessary details. Here we talk about some principles. When we do theoretical analysis, we follow some principles. This is the first principle we need to follow. ignore unnecessary details. There are many details, but not that important, so we can ignore. So let's look at what kind of details we can ignore. First, we start with this approximation formula we got last time, and we record the meaning. T, running time function, C of n, number of basic operations, the constant C op, cost of a basic operation. Here, when we talk about the cost, we mean execution time. We pay that cost. We pay that execution time as the cost. The approach we do, remove unnecessary details to reveal the most important factor. That's the high-level principle we will use. For the low-level details, we need to answer some questions. First, can we ignore some constants? In our formulas, some constants. Can we ignore some of the constants? Right? So that's one. Can we ignore some minor terms? Major terms? We have many terms. Some of the terms are major terms. Some of the terms are minor terms. Can we ignore those minor terms? That's the questions we need to answer. All right. First, let's look at this formula. When we do the ratio, we double the problem size, double the input size, 2n, n. Then we take the ratio of the running time function. We also take the ratio of the count function, C of 2n over C of n. You can see that cost C op constant cancel out. So you can see, this simplifies the expression. So that number is not important, cancel out. Now we want to see when the input size doubled, how fast is the growing rate? How fast? How many times it changes? That can tell us some information. How fast is the function, growing? All right. So you can see in this ratio version of expression formula, the C number is not that important. That means we can ignore it. Under certain situation, we can ignore this constant. This constant. All right. Then minor terms. What are the minor terms? What are the major terms? So we want to compare that. When we do that, let's use some concrete example we just learned in the previous video. Use growth function to measure efficiency. In this part, we need to talk about a new concept called a growth function. What is a growth function? So let's continue our discussion from the previous half. What is the major term? In our module 1, we learned a concept called a dominant term. So remember, when we do the analysis on the linear search or sequential search, we derive a formula. After we get that formula, then we look at its dominant term. Look at that. So the major term, we can use the dominant term to represent the major term. We want to use it. Yeah. Record the selection sort. Yeah. Our data given in this array. Then we do the sorting. Yeah. Many rounds. Each round, we put one element in place, another element in place. Okay. Finally, we put all elements in place. At the end, we calculate the total number of comparisons. And after that, our conclusion, so we can say for these three cases, best case, worst case, average case, the answer, number of comparisons, always this number. Yeah. Right? Always this number. Yeah. Because there is only one case. You have to go through all the way from beginning to end. Okay? From your starting point, every time when you do a scan, you need to complete at the end of the array. Yeah. So one case. That's the same best case, worst case, average case. Yeah. Now let's look at the expression numbers. The number there, if we multiply them out, we get two terms. First term, second term. And we say the first term is the dominant term. Okay? Dominant. The first term dominates the second term. How can we see that? How do you see the first term dominates the second term? Let's view that using the following formula. We take the limit from calculus, 1800, math 1800. Yeah. When we take the limit of the ratio of the first term over the second term, after the simplification, we just take the limit of n, and when n goes to infinity, its limit is also infinity. You can see the ratio approaches to infinity. Can we say the first term dominates the second term? Yes. Infinity, definitely it dominates second term. Yeah. So that's the way we view the dominant term over other minor terms. Yeah. Finally, as the conclusion, remember here we ignore that constant. Here we have that constant 1/2. When we consider the most important part, remember in this ratio the constant is gone, so we can ignore that constant. So we get n squared after we ignore that constant. This is the concept of the growth function. So the growth function, we ignore the leading coefficient. That 1/2, the leading coefficient, we do not need to consider it. Yeah, the reason, because in this ratio, we do not need it. Okay? Yeah. So that's the concept of the growth function. So I emphasize that, yeah, because based on my experience last semester, many students, when I ask them to give me the growth functions, they still give me the coefficient number. So we don't need that. When we talk about growth functions, we do not need to include any constant coefficients. All right, so we complete this part, 8.2. Oh, 8.3, I think, right? Yeah, 8.3, yeah, we already, 8.2, yeah, so this is growth function, 8.3, yeah.